May 18th, 1980. So the north flank of the mountain blew out and created a massive empty crater, which resulted in a forever changed landscape. So this is just a pretty historic photo of the pyroclastic, the ash plume going up. And then Mount St. Helens is located in between Olympia and Portland, right here. Okay, so this is Mount St. Helens before the eruption, and then this is Mount St. Helens after the eruption. And so our samples were mainly collected in 2016 in this region here. So the objective of my research was to determine the relative resistance of the different rock types of Mount St. Helens. And so I identified rhyolite, andesite, pumice, scoria, and granitoid. And then I was trying to see if identifying the presence of easily weathered minerals such as calcite and apatite. So looking at the after product of my experiment and identifying if those minerals were there. And then I wanted to see how the chemical weathering of the minerals affected the stream water chemistry in the nearby streamways. Another just main thing was just to observe the weathering processes of relatively young deposits. In geology, we mostly look at things that are really, really old as far as time scale goes. And so to look at something that was deposited in our lifetime is something and what we wanted to do. So I'm going to be talking about leaches. This is not to be confused with this little guy here. Leach is going to be a solution, a liquid solution here, and then that guy is not what we're talking about. So here's just a photo of the different rock types. So rhyolite, granitoid, andesite, pumice, and scoria. And then some samples. So my samples were just in a plastic baggie with the fine grain and large rock fragments, well, small rock fragments. And then I sieved these down to less than 2 millimeters. And so for the rock fragments, what I did was I crushed them using a steel mortar and anvil set. And so I placed the rock fragments and their powdered form here, just so you can see the process in which I changed them to use in my experiment. Okay, so my methods. So I processed the samples, which we saw, and then in a sequential step, I added the leachates. And so my 3 leachates were ultra pure water, acetic acid, and 1 molar nitric acid. And so first I would add the leachate to my solution in a centrifuge vial. I placed that on the rocker table overnight, came back, centrifuged it down, and removed the leach. And so my process from removing the leach is really similar to just doing a pour over coffee, but more scientific. So we have a funnel set up here with a filter. It's a 45 nanometer filter that I pour the leach into the funnel, and then it collects down into the polypropylene bottles here. And so the reason that we are filtering them out is that we don't want any solid particulates going into our ICP. And so the last part is to analyze the solution using the ICP, and we're looking for elemental concentrations. So here's just some more pictures. These are the centrifuge vials and then the preserved leaches there. So I did have to preserve our water leaches to make sure that they were acidified enough, one for the background calibration for the instrument, but also so that nothing strange is growing in my samples. So ICPOES stands for Inductively Coupled Plasma Optical Emission Spectroscopy. It measures light produced by energized atoms or ions, and then each element actually has a specific wavelength pattern, and that allows us to measure the elemental concentrations. So this is currently set up in our old geochemistry lab. We are now getting a new one, which I got to see, and it's really cool. So this is the ICPOES, And then this is an auto sampler. So we place our sample vials on there, and then they get sucked up through this tube, come down, and get analyzed into the machine here. Okay, so here is just an example of what possibly the ICP can tell us. So you see that we're looking at the elemental concentrations here. And then we have it broken up between my water leaches, acetic acid, and then my nitric acid leaches. And so the main takeaway from this image is that each step of the sequential leaching process progressively got stronger, as in each leach was removing more from the sample and had a stronger ability to break down the rock. And so water, we are mostly seeing sodium and silicon. So sodium, we can assume and interpret that that's coming from salts. In our acetic acid, which is also known as vinegar, and that's mostly removing calcium, and we can interpret that as the calcium carbonates coming off. And then our nitric leaches is going to remove some calcium, magnesium, silicon, aluminum, and iron. So we have a much broader range of things being removed here. And then we can also look at the concentration side over here. And so we can see that a larger amount of things are being removed in the nitric acid. We can go up to 5 milligrams per gram of rock here, whereas the water is only 0.90 milligrams per gram. So we have water, then acetic acid, and then the nitric acid. And then I also was able to do a literature review and look at different research that has been done in the area. So in Hinckley and Smith, 1987, they were mostly looking at ash, fresh ash collected during and 1 week after the eruption in 1980. So their elemental concentrations are much, much higher than mine. And so that might be like, okay, well, is that really what you wanted to see? And it is what I wanted to see. So if my elemental concentrations were at or near the concentration seen in Hinckley and Smith 1987, that would be a call for a red flag warning. So I would have maybe possibly done something wrong, or something weird was going on. And the reason for that is that they were looking at fresh ash deposits that hadn't been exposed to any sort of weathering or elements outside. So mine were old weathered samples. I mean, I crushed them up to expose fresh surfaces, but we wanted to see that there was less, but the similar elements being removed. Okay, so then I also kind of did a analysis thinking about what different minerals exist in igneous rocks. And then I did a little plot diagram here. Okay, so in plagioclase, there's calcium, sodium, aluminum, silicon. And so thinking about which minerals are contributing what elements, I want to go back and look at, okay, in my analysis, I'm seeing X minerals. Could this be backtracked to any of these minerals here? Here is a graph of the ways the different rock types looked after the ICP analysis. And so I have andesite, scoria, rhyolite, pumice, granitoid, and then this is just the different patterns that were produced. The reason for breaking them up into the different rock types like this is to observe when we obtain enough samples ran, if we can establish a fingerprint for each of the rock types. So when we look at the water chemistry, if we can say, okay, well, we're seeing this relatively seeing this fingerprint in the stream water chemistry, could it possibly be coming from andesite or rhyolite? So a summary of my research, the focus was to determine the relative resistance of the different rock types in Mount St. Helens, and then identify the presence of easily weathered minerals such as calcite and apatite, and then examine how the chemical weathering of minerals affect the stream water chemistry, and then also to investigate the weathering processes of relatively young deposits. So what's next? I'm still in the process of determining what minerals are breaking down I thought it was going to be something that was just really straightforward, and it turned out to not be that way, that happens. And then I'm also still needing to compare my data to the stream water data to observe what minerals are contributing to that chemistry. A really great thing is right now I'm taking geochemistry, something that I didn't have in my belt when I was doing this research. So I'm hoping that after that class, I have a better understanding of the science behind it, and I can better make these comparisons and analysis. And then recently, as of last week, we sent off some of those fine grain samples in the original vials to WSU for XRF analysis. And this is just going to give us an idea of what possibly what minerals are in those fine grain sediments. And then this was thanks to funding acquired through the EWU Alumni Research Grant. So we'll talk about some grants later. And then I am working on my undergraduate thesis. So all of this research has been written up in some form. And then I'm working on basically polishing that off and compiling it into an undergraduate thesis. So we're going to transition over into the McNair side of this presentation. So how was I able to find undergraduate research opportunities? When I transferred over to Eastern from Monterey, California, a community college there, I needed to go to graduate school because I had it in my head that I needed at least a master's degree to do anything of significance with my science degrees. So at the time, I was taking Geology 121 with our very own Professor Keach. I told her about my dreams and goals to attend graduate school, and then she introduced me to Dr. Nazat. After talking to Dr. Nazat, she said it would be a really good idea if I went that day and talked to the McNair Scholars Program down in Monroe Hall. And it turns out that they were still recruiting for McNair that quarter, but I only had a week to get in my application. So that was that. So the Ronald E. McNair Postbaccalaureate Achievement Program, that's the official name. So it is in honor of Ronald E. McNair, who was the second African-American to fly into space. Unfortunately, he did pass away with the explosion of the Challenger. And then this program was inducted in for his honor. And then the goal is to encourage low-income first-generation college students and students from historically underrepresented ethnic groups to expand their educational opportunities by enrolling into a PhD program and ultimately pursue a career in academia. So the application process. So like I said, I only had a week to do all this, which is not typical, but it was good. It was a good learning experience. The application process for McNair mimics applying for graduate school, as this is the main goal of the program. So you have to conduct faculty interviews. So I conducted an interview with Dr. Nazat, of course, but I also wanted to see what else was out there. So I also interviewed Dr. Love from the chemistry department and Dr. Camille McNeely from biology. They all were really enthusiastic about the research that they had to offer, but I ended up going with Dr. Nazat. And another thing in my application was a statement of purpose. This is something required for all graduate applications. So that's just telling them a little bit about you and a lot about what you want to do, what research you're interested in, and what you plan on doing with that research, mainly a career in academia or industry or service. It includes transcripts, 3 letters of recommendation. This is something that you want to keep in mind when you're thinking about going to graduate school, or even if you're applying to internships. Letter of recommendations are very common. For McNair, they wanted letters of recommendation from people who had PhDs. At that time, I had only attended Eastern for 2 quarters. Actually, I think it was 1 quarter. So I didn't really know anyone. So I used letters of recommendation from my previous institution, my community college. And then Dr. Nazat, who didn't know me very well at the time, requested that I provided her work samples to prove that I was ready and up to the challenge of undergraduate research. And then also you must have a 3.0 GPA to participate in the program. So once you get all of these application components in, you turn it in, this pretty little package that you work so hard on, and then you have to wait. And this is very much the same with graduate applications, and I can tell you firsthand because I'm currently in the waiting process for those. So the application process was hard, and then came the, so I had to, Dr. Nazat was, and she provided me with all of these ideas of things that she was interested in. She wanted to, have somebody look at. And I really ultimately decided on the Mount St. Helens project because I liked volcanoes. So that's where that came from. So then I had to build a background for the project, and that required reading lots and lots of academic papers, something that I hadn't really ever done before. So I had to learn how to do that efficiently. It was pretty overwhelming, but once you have read, I would say 50 papers, you start to kind of like get into the groove of reading them. I did 2 summers of research with McNair and working with Dr. Nazat. And then I also worked in doing private independent study on my project with Dr. Nazat in the quarters between those 2 summers. And then I applied for 1 additional grant application to fund my research, and that was that EWU alumni grant. And that was in order to send those samples off for XRF analysis. I was able to present at 4 conferences and then 2 talks, including this one. And then I have applied to graduate programs and am currently applying to graduate programs. And then my undergraduate thesis is in process. So that one little conversation that I had with Professor Keach turned into kind of like my life and journey at Eastern. So moving on. So it seems like that was really stressful. There was a lot involved. The application process was pretty difficult, and then like I didn't really have a lot of time to do it. And then I had to spend my summers doing this research, and was that fun type of thing? And then yes, it was awesome. So one thing about undergraduate research is that not everybody gets to do it, especially at larger institutions. Such as WSU, it's not super common, and then it's more competitive to do undergraduate research. I was also able to learn geochemistry as I was learning chemistry, and then I familiarized myself with multiple laboratory instruments such as the ICP, centrifuge. I was able to learn methods that I can apply in future research at graduate school and my future career. I built lifelong mentorships, not only with Dr. Nazat, but with the people in McNair. And then I was able to meet professors from other institutions as well. I was able to learn self-care and stress management through it all. This was something that I wasn't really attuned with. And I think, I don't know if Dr. McKenzie's here, but I went to her one time and I was like stressed out. I was like, why am I even doing all of this? And, there's a purpose there. You're stressed out and you get through it and you're better for it. And so that was something that I did really have to learn. And then I learned what it took to be successful in graduate school and how to apply. And that was really all thankful to the journey as a McNair Scholar, but then also the McNair program itself. There's a lot of side education. So you're not always in the lab doing research, you're also in the classroom learning about statement of purposes and what that means, learning about how to write professional emails. We even did a trip to WSU pre-COVID and learned about etiquette and how to conduct yourself when you're in a room full of professional people. So is McNair right for you? So some of the criteria for McNair is that you are traditionally low income, first generation student, underrepresented student, you want to go to grad school, and you want to give back to future students and provide similar/better opportunities. This isn't written as one of the things, but I think that this is really important. One of my main reasons for wanting to go into academia is because I didn't have any academic or positive role models growing up. I had people who helped me survive my childhood, but I want to give that opportunity to students like me as they're going through community college or as they're going through their undergraduate to, to tap on their shoulder and say, hey, I see promise in you. Things are, you can do something different. You can do something great. And here's an opportunity. I want to be able to be that person who grants opportunities. And then another thing I really wanted to address in my future career is the I struggled, so you must struggle too mentality. I think, especially in STEM, in my experience, this is something that is pretty prevalent, unfortunately. We all have different learning styles, but also we're all human. And so I want to be able to be a professor who is understanding, but also is going to make sure that you get your butt into gear and get through the finish line and, learn the things you need to learn, but also with having a big heart. So if you looked at that list and you don't qualify for McNair, how else can you perform research? So the first step is to talk with your professors. You can also apply for grants. The CSTEM has a grant for undergraduate research. Our department has one. And then talk to your professors again. That's on there twice because that's twice as important. You're not going to get into these research opportunities. You're not going to get any sort of internship opportunities if you're not talking and communicating with people, letting them know that you have the drive to do this research. So that's really something that you need to take upon yourself and reach out to these professors. We have a really great diversity of staff in our department, and they're all doing really great research, have really awesome research. One has the ability to go up and talk, I want to do this happen. Of the ways to make it happen. An acknowledgement to my full mentor. And then a special thank you to the McNair Staff Center, working through research this and graduate applications, is that I have to have. So I'm just gonna stop the share and